So good morning, students. So after 1 week, we are going to conduct the class of the fluid mechanics. So let us in the last class we have completed the manometer properties of the fluids. Today I am going to the start kinematics of the fluid. Is it visible or not?
Yes, sir.
Okay, thank you. So let us see the kinematics. So velocity field, when we are considering the fluid with some velocity, with fluid that is the with motion, means when we are talking the fluid in the motion means fluid that is the contain some control volume, not a particle. And when we will discuss the fluid dynamics means related something that is the play the role of the force. So kinematics generally we will discuss the geometry, that is the geometry, different types of the geometry through that the fluid kinematics or velocity analysis we will perform. So there are two approaches. First one is the Lagrangian and second one is the Eulerian approach. Only by these analysis we have to analyze the fluid mechanics. Out of these, that is the Lagrangian. Lagrangian analysis tracking individual fluid particles means we are the observer, we are the analyzer. We have to analyze the fluid. Then we are treated as a observer, analyzer. So we have to move with the fluid particles, and that such type of the analysis is called Lagrange. In that situations, we are that is the follow. We only follow the one particle of the fluid. In that situations, that is the particle positions, we are the interested in the velocity of the fluid, so we are interested the vector for the Lagrangian approach. Then position vector of that is the velocity is nothing change in position divided by the change in time, and time elapsed tends to 0, and our space coordinate x y z and the unit vector I j k, that will be the velocity of that particle which we have following, which we are follow. And this is the Lagrangian, but the motion of one particle is insufficient to describe the flow field. So the motion of all particles must be considered simultaneously, which would be a very difficult task. And a spatial gradients are not given directly. So Lagrangian approach is only used in a spatial circumstances or molecular dynamics or mechanics. In Eulerian approach, focus attention on a fixed point in a space means we are interested to analyze the fluid passing through the any system. So we will take a control volume. We will take some fixed domain, and in that domain we will focus. In that domain, and we are observer, analyzer. We will only stationary, and that is the study that control volume, and that control volume which we have selected for the analysis represents the whole fluid fluid domain. Means we will take a contour of the fluid and analyze that. And this approach, that is the in a fixed position, that is the, so x is three positions, then velocity in these situations, velocity, that is a function of a space as well as temporal time, velocity component. So and v, that is represent the generalized velocity vector, equal to the ui plus vj plus wk, where u, v, w are the velocity components along x direction, y direction, z direction. I, J, K are the unit vectors along x-axis, y-axis, z-axis respectively. This is the general trend. A small u represents the velocity vector along x-axis, a small v represents the velocity along the y direction, and a small w represents the velocity component along z direction. This is the general, that is the notations. And capital V, U, all these represents a velocity vector unless until it is a measure. So a small v, u, it is a velocity, also a function of x, y, z, and t. Still, a small u is a component of the velocity along x-axis, but it is affecting also, because our fluid which we are analyzing is a continuum, not is a particle. It is a, we are assuming this is the continuum. So continuum affecting also the other axis. In Lagrangian, particle is moving, particle, not fluid is moving, but particle, a particle of the fluid. And in the Eulerian, we are assuming some part of the fluid, which is a continuum. So affecting the also other direction, means velocity in the u along x-axis, also it affects on the y direction and z direction with respect to, that is the time. So that's why we are talking u, v, w, all are the function of x, y, z, and t, not only x and y and z. So the approach is usually interested the flow field in some region, means what we have selected for the analysis, not the history of the individual particles, from where, from when it will start to move the particles, that is not required here. So the control volume in generalized for contour, control volume, selected region, we are telling used to say control volume, which you might be read in the thermodynamics. And here I have shown in the term of x, y, z only. This is the Cartesian coordinate, but we have to also study the same analysis in polar coordinate or cylindrical coordinate and a spherical coordinate. And that is the Cartesian coordinates, cylindrical coordinate, spherical coordinates, all are interrelated, and that is called orthogonal curvilinear coordinate. You can transform from one coordinate system to another by the orthogonal curvilinear coordinate system. So this is the all about the hour. So in the whole fluid mechanics, we will analyze on the basis of the Eulerian method, not Lagrangian. Not Lagrangian is analyzing for a fluid particle, a simple a particle of the fluid. In the Eulerian, we are analyzing a contour or control volume of the fluid, whatever may be number of the fluids available or particles available. So we will prefer that is the Eulerian methods. See, acceleration of a fluid particle, that is nothing rate of change of its velocity. So velocity in the Lagrangian particle function of the time only. So we have to describe motion in term of the position vector. So RP, this is the position of a fluid particle, and that represents x, y, z of that particle, and itself it is a function also depend on the time. So velocity is position with respect to time that give the particles velocity along x-axis, y-axis, z-axis. It is written in the unit vector form. Acceleration change of the velocity with respect to the time that will give acceleration ax, ay, az. Sub suffix give the acceleration component along that direction. So acceleration along x-axis, du of the particle by dt. In Eulerian approach, velocity is a function of both a space and time, because we are considering some area, some zone, some contour, some control volume in that fluid. So see, velocity u is a function of x, y, z, and t. V is also function. Here, for the simplicity, we are analyzing the Cartesian coordinate. It is not valid for the Cartesian. It is also valid for the cylindrical and spherical coordinate. Always remember. So acceleration is dvy dt. Acceleration ax, ay, az, like that is the in Lagrangian. See, interesting thing is here. Acceleration along the x-axis, ax, subsuffix that is the x, du by the dt, previous by the particle, for the particle, du by dt for particle. Here for the control volume fluid, this acceleration is valid, which we have selected the zone of the fluid is valid. So du by the dt means total derivative of the velocity with respect to time. D is the total, and from mathematics you might be know it is the combination of partial. So u is a function of x, y, z, and t. When we will apply the calculus of the differentiation, that will come out partial derivative del u by the del t plus del u by the del x into dt plus del u by the del y into del y by dt plus del u by the del z into del z by the d, and del xy, the del t is nothing but the velocity along x-axis. Similarly, del y by del t is velocity along y direction, and del z by the del t is velocity along that is the z direction. So this will acceleration along x-axis that will takes the form del u by the del t plus u del u by the del x plus v del u by the del y plus w del u by the del. Here we have written from the calculus point of view. You may also develop this equation from the physical interpretation, which I will discuss in the seventh semester in the computational fluid mechanics or fluid dynamics chapter. You may also, that is the physically, that can interpret how one fluid move from one position to another. So see, the acceleration having that is the two parts, and this du by the dt or same thing is written capital du by the dt. Derivative is written in capital or full form, that is the here, that is the both are the same thing, and this is the sometimes called total derivative, substantial derivative. This is the generally term used in the mechanics or fluid mechanics, the computational fluid dynamics, substantial derivative. So substantial derivative of the velocity component along x-axis. Similarly, the acceleration component we can write in y direction and z direction. See, the small u is replaced by the small v that give the acceleration along y direction. Similarly, the v is replaced by the small w, give the acceleration along the z direction. Rest system of the equations remains same, such as first del y del t. This is the our tool, partial derivative tool. When we are interested to find out acceleration along y-axis, we will insert v, del vy del t. And rest third term, u plus into del y del x plus v into del y plus w del y del z. These tools remain same. So there are two components. See, this is the two. First one is the partial, second one is the velocity width, that is the its gradient. So u into del y del x plus v del y plus w del y del z is common in all three equations. If you are interested to find out acceleration along z direction, then we will insert the velocity component w. So this will give del w by the del t plus u del w by del x plus v del w by del y plus w del w by del. So this is the two components. First one, see the when we will write in generalized term or vector form del dvy dt equal to the del vy del t plus v dot del v. V underscore, that is the velocity vector, not velocity component along y-axis, but it is the velocity vector that having three components: u, a small u, a small v, a small w. So this is the our acceleration, total derivative or substantial derivative term. Out of these, see, first term del vy del t is called local acceleration, temporal acceleration, local or temporal acceleration. When we are talking acceleration along x-axis, this will become del u by the del t. When we are talking about the z direction, This will become del W by del T. When we are generalized writing in general term, then del capital V by del T. But this is the nothing but the local or temporal acceleration. Second, three terms u del y del x plus v del y del y plus w del y del z. This is the your core convective acceleration. This is the sum change. That is the called convective acceleration. First one, acceleration due to the temporal time. Second, due to the position change from one point to another point. That is the convective acceleration. So, general acceleration is nothing but a summation of local acceleration plus convection or convective acceleration. First one with the temporal gradient, second that is the last three term may be the spatial gradient, and all these we are considering the convection. So first one that is the due to the steady, and second that is the unsteady when we will discuss means time to unsteady, and second one this changes in convection is due to the non-uniformity through which fluid passes. So uniform, non-uniform, steady, unsteady, all these are we have to discuss. So this is the our total acceleration, derivative acceleration. When we will discuss about the fluid mechanics, this acceleration we have to consider, and different situations will give the different that is the ideas. So before going to the continuity equations, here I have that is the written continuity equation in three dimensional. So before to the continuity equations, I would like to brief some terminology which we have to use in the fluid mechanics. Let us see just I first one, a streamline and a stream tube. So a streamline and a stream tube. So a curve formed by the fluid vectors of each fluid particles at a certain time is called a streamline. So for a particular line, that is the time a fluid follow a that is the form a curve or moving from one point to another point, that is the follow some that is the certain time, that is the velocity vector. So a streamline in some system fluid flow in a straight line or in a curve, that is not a matter is it is not mixing, it is not zigzag, it follow whatever we have allowed or given the path for the flow. In other words, the curve where the tangent at each point indicates the direction of the fluid at that point is a streamline. So tangent at each point indicates the direction of the fluid at that point is a streamline. So a streamline is obtained by drawing a curve following this flow. So from the streamline, velocity vector has no normal component. This is the important. In a streamline, the velocity vector has no normal component. There is no flow crosses the streamline. Then this is the identification if flow is a streamline or not. So no flow which crosses the streamline. Flow that is the two-dimensional when we are considering then gradient of the streamline dy dx velocity in x and y direction as u and v in the streamline obey these equations del xy del xy the u equal to the del y by v or dy the dx equal to the v by u where u is a velocity component along x-axis, v is the velocity component along y direction, dx is the a small element length along x-axis, dy is the a small fluid element length along y. Then it is the relations exist if any flow follows the streamline flow. dy dx vyu are the fluid element's length divided by its velocity. So see here, so the certain point that is the some streak line. See, so line which show streams include the streak and path line. So by the streak line is mean the line formed by a series of fluid particles which pass a certain point in the stream one after another. And here that is the die is shown, or you might be seen a very that is the simplicity, however it is the restricted the smoke of the cigarette follow a streak line that gives the flow direction. On the other hand, the path line, that is the particle starting from one particular point in a stream and traces the path that gives a path line. So with the streamline, path line, a streak line, we will discuss some examples, then you can clarify mathematically. So in the case of a steady flow, see, a steady, unsteady. A steady means flow doesn't depend on that is the time. Doesn't there is a no restriction on the flow with respect to the time. A steady means del y del t tends to 0. That is the time relation derivative. If it is unsteady, if it is a transient, then del y del t term will exist in our equations, in our relations, in our that is the analysis. So a steady means it doesn't depend on the time, or mathematically del y del t terms 0 means local acceleration, what we have discussed in the that is the material derivative or acceleration, that term will become 0. So in the case of a steady, the three kinds line are coins. One coincides means a streamline, a straight line, path line. It means that it differentiates only due to the time factor. That's all. And that is the different, that is the streamlines when we will compile or collect, that will give a stream. So that is the steady what we that is the velocity pressure and at any position does not change with time. So our field variable is independent of the time, otherwise change that is unsteady. Flow may be three-dimensional, two-dimensional, or one-dimensional. So if it is the three-dimensional, it depends on the x, y, z, or that is the all three space. If it is a two-dimension, it is only function of x, y, t, or y, z. Any two. It is not always sure कि only x, y we will consider. Any two that is the space we will consider y, z, x, z like that. Any not but three. So in one dimension that is we are considering the flow, accelerations, field variable, only the analyze only one space. That is the either x coordinate system, y coordinate system, z coordinate system, or in the polar or spherical or theta z. It is only depend along the z, along the radius or angular. That's all. So that is the simple situations when it depends or it is the field variable changes along the x-axis or y-axis or z or only one x. That is the independent variable is 1. That's all. X, Y, Z is independent. U, A, P, all these are the dependent. So independent variable is only 1. That's all. Either R, theta, Z, or omega like that, any coordinate system. So this is the one dimension, two dimension flow like that. Laminar flow. See, this is the tested by the O Reynolds. That's why sometimes Reynolds number that is the classify or differentiate that number the laminar flow or turbulent. It is the first that is examined by the Reynolds. So a color liquid led to the enter the a glass tube. That is the shown in the figure. The valve was gradually opened by the handle and the color liquid followed as shown like a piece of the thread. See, there is a continuous that is the in a thread like without mixing with the peripheral water. In a straight like a thread. Such flow is called laminar flow, and this you have to test also in the experiment. Also, you have to check in the experimentals when the flow velocity of water in the tube reaches certain value. Means we are open the valve of the water flow. Observe that the line of colored liquid suddenly became turbulent, means milling of the peripheral, means it is not follow that is the flowing in a straight line or like a thread. It is the thickening or it is the mixing or it is the giving some this and that. So the flow velocity at that time when laminar flow had turned to the term of critical velocity. So this critical velocity, after that the transition and then limit turbulent flow takes place. Reynolds actually in his experiment shown that he, from a particular Reynolds number, the flow will become transition or turbulent. That number is called Reynolds number, and this is the some ratio rho v d by mu, where rho is density of the water or fluid, rho V is the velocity simply, or D, diameter of the pipe, and divided by mu, viscous by inertia force, that is the, so divided by the mu is viscosity, that is the dynamic viscosity. When we are talking simply viscosity, it means always dynamic unless until we will add kinematic viscosity. So dynamic viscosity. So Reynolds number is represented by the capital R and a small e. R e equal to the rho v d divided by mu. This is the that is the formula given by the O Reynolds. See, D is the diameter of the pipe when flow takes place through a pipe. Otherwise, non-circular pipe we will select, then D will become hydraulic diameter. So hydraulic diameter you might be aware or not aware. I will discuss when I will teach you the channel or flow through the open or closed channel. 4 into the cross-sectional area divided by the weighted perimeter. That is called hydraulic diameter. If flow takes place through the flat plate, this is the all these situation for the closed flow. When flow through the open channel or flow over a flat plate, then D is replaced by the L. L is called characteristic length of the object over which flow takes place. So in the case of the closed flow, D, and open flow we will take L. D is replaced by the L. So flow through the pipe, Reynolds number is up to 2300. Flow is treated as laminar. Flow is treated as laminar. After that, 23 to 25 to 28, 27, the transient, and after that it is a turbulent fully. But we will only at this level because we are the beginner of the fluid mechanics. Just we will consider up to 2300 flow is called laminar if Reynolds number is 2300 when flow takes place through the pipe or circular diagram. For the flat plate case, the this number Reynolds number is equal to the 5 into 10 to power 5. 5 into 10 to power 5 is laminar, and more than that means 5 into 10 to power 5 flow will becomes or called turbulent. So these are the selection or clarification about the laminar flow, turbulent flow, flow through the pipe or closed duct or open channel or through the flat plate. All these are numeric value you must remember or you must know about the fluid in the fluid mechanics because that is a very important parameters. Laminar flow, turbulent flow, flow through the pipe, flow through the open flat plate like that. So these are the here I try to show some laminar flow, turbulent flow, then incompressible and compressible fluids. You might be aware it is the compressing when you are pumping the tube or tire of the your motorcycle, that is the motorcycle or cycle in the childhood. You might be say air is compressed or it feel like some heat. But in the mathematically I would like to say the general fluids are incompressible, which is we are using day to day, but the gas are generally compressible. But mathematically, if density remains constant, is incompressible, density changes with a space or time and a space, it is a call that is a compressible or not changing, means incompressible. Then density we can take outside from the our derivative from the our differential equation. It means it is a compressible. At the level of the UG, generally we will discuss the incompressible fluid. Generally, however, you might be know it is a function of the temperature. It depends also on the pressure, but temperature is more prominent in the case of that is the gases. So incompressible means density remains constant throughout our analysis, throughout the system. It doesn't depend on the space or time. Then rotations and a spinning of the liquid. So let us see up to these here rotation and spinning we will later on come on because it is the some important for derivation. Before going to this compressible incompressible, I am going to start the continuity equation because we have derived that is the continuity equations here I have taken in 3 dimensions. See continuity equation, then we will go to the 1 dimension. So first we have chosen a fluid element whose length is dx, dy and dz along x-axis, y-axis, z-axis respectively. See, all of you listening or not listening or sleeping?
Sir, we
Hello?
are listening. We are listening,
Ah,
sir.
okay,
We are
okay,
here,
thank
sir.
you. Okay, thank you. Because one-sided we are speaking, that's why. Okay, see, this is the our fluid element. Just see the figure. Here I have shown a fluid control volume taken. And for simplicity, we have chosen that is the Cartesian coordinate. Otherwise, no meaning. See, in the control volume, this is the taken. Left side, so see the left side that is the fluid is entering with velocity u and its property is density rho crossing the cross-sectional area dydz. This area crossing entering the surface is dydz and due to the fluid element dx leaving or exiting right side. As I told you also in the last classes, it change. That change due to this fluid element, and from that is the Taylor series we can write initial was rho into u due to the fluid element length dx. From the Taylor series we can write del y del x into rho u into dx plus cross sectional area through which it exiting dy into dx. This similarly y direction and z direction and our axes are always taking as per that is the convenient. Right side is the plus, left side is the minus, top side is plus, bottom side is minus. Means flow takes place from left to right, top, that is the bottom to the top. According to the axis, flow will exiting. That's all, entering and exiting. Then from the definition, the rate of change of a mass in a volume element. Again, I am reading. The rate of change of mass in a volume element equal to the summation of the mass fluxes into the volume means entry. First summation that is the for entry minus exiting. the summation of the mass fluxes out of the volume element. One is the entering in the system, means our control volume which we have chosen for the analysis. Second, that is the left is the entering, right is the exiting. Bottom is the entering, top is the exiting. This. So see, mass. So as I told you in the fluid mechanics, directly mass we have not to use it. We will use in the term of the its property, means density. So density into that is the volume. Volume is written in the term of the area into velocity, and velocity written x dx by dt means flow in term of the time. That's why rate. So that is the, see here figure. Its edges have length dx, dy, the mass flux, the mass flux rho into u into dy into dz. Mass flux flows in through the left surface of the volume element with surface area or surface dy dz. The quantity rho dot u density into the velocity changes its value from position x to position x plus dx, and this change position is called x plus dx minus x, that will become dx, length of the filament. So from position x to x plus dx in x direction by del y del x into rho into u and overall into dx. This is the change due to the dx, x plus dx. Therefore, the mass flux exiting the volume element through the right phase can be written as rho dot u plus del y del x into rho dot u into dx and overall into dy dj. See, so in the y and z direction, similarly, we can write when we are treating or considering y direction, then cross-sectional area is dx dy z. When we are considering z direction, dx dy. So according to the condition of mass, that is called continuity equations. The rate of change of mass inside the volume element under the consideration corresponds to the difference between the mass fluxes entering and exiting, means influx. Exiting, that is the entering and exiting, is known as influx. Then this, so rate of change of mass. So del y del t is the rate. Mass rho into dx into dy into dz. So density equal to the mass by volume, that will become rate of change of mass equal to the right side, that is the influx. So rho u is cancel out, that will become u del. So this same equation, that is the dx dy dz is not a function of t, so take outside, then that is the right side. mathematical expression for rate of change of mass in the volume element. So del y del rho t dx dy equal to the right side influx along x-axis plus y-axis plus z-axis means entering minus exiting along all three axes. So rho u into dy dz is entering. Leaving from the fluid element along x-axis is rho dot u plus del y del x rho dot u into dx and through the area dy into dz. Similarly, y direction when we are talking y direction means area is dx dz. Other than that, when we are considering z direction, other than the fluid element dz, we multiply dx into dy. So velocity along y direction, u is replaced by the v and v is replaced by the w. This simple case. This leads to that will come in the minus form right side. When we will transfer to the left side, it will become del rho y del t plus del y del x rho into u plus del y rho dot v plus del y del z rho dot w equal to 0. See, this equation is generalized continuity equations for three-dimensional unsteady compressible flow. Till now here that is that we have not touched anything. Nothing we have changed. All we have taken from so density is inside the that is our derivative temperature that is time term is available and it is the three-dimensional all so this is the generalized continuity equation. It is valid for three-dimensional, unsteady, and compressive. When we are treating a special case, incompressible, here see, when density remains constant, its derivative with respect to time also zero. So for incompressible, first term automatically become that is the steady. Or when you are talking about the steady, then also first term will become zero and density remains inside the derivative. But it is incompressible, so density remains constant, so that is the take outside. So generalized equation for that is the our continuity equations is del rho y del t plus del dot rho dot v. V here is the bold, that is the darken, that is the velocity vector, not velocity component along the v direction. Here that is the symbol, that is the v equal to 0 or for the compressible flow del dot v equal to 0. So this is the our continuity equations. In generalization form, we will use to write in tensor form ui xi ij k means I that is the velocity component along x-axis, j along y-axis, k along that is the w-axis. All these are the notations the written in the textbook. A special case, a steady one dimension flow, mass flux, say a steady. So del rho y del t that term will become 0. Entering equal to that is the leaving, this will become 0. So rho 2 u2 a2 minus rho 1 u1 a1 equal to 0. Mass flux out minus mass flux in. So a steady flow is one function of spatial this And this is the our continuity equations in the term of the Cartesian coordinate. Here, cylindrical coordinates are also given. About the coordinates you might be aware, but that equations is also given del rho by del t plus 1 by r del y del r under bracket r rho vr. Vr means velocity component along the r. V theta velocity component along theta. Vz velocity component along the z direction. So these are the three components. It is given by the sub suffix r theta z. In the that is the Cartesian coordinate, simply we are using u, v, w. But in the polar coordinate, we is generally used by the its sub suffix. So up to here today, I am going to stop. If you have any query, then ask me. In the next class, we will see the rotations, the rotational flow. All still that is we have not completed. So this is the our kinematics. Is it correct? And as I hope कि maximum students are attending the classes, so here that is the 90 is showing. So let us see that is the all are the present. Sometimes I will take the attendance and check it. So about the attendance, don't worry. Must take the advantage of the classes and try to attend the class. I will give the lecture notes after completing the class, and examples we will discuss in the class. Yes, any query then ask me, please. Home assignment I have given or not? First home assignment, Saurabh, Mr. Saurabh, I have
No,
given
sir.
or not? Not given.
No,
Okay,
sir.
okay. In this week, that is, I will send you, and you try to complete the home assignment timely and send us in a zip file or in a combined form. Is it correct? So that's why you may get the exposure of the numerical problems. I hope we should will reopen that is very soon, but still we are on the online. Let us see what happens.
Sir, please share this PDF too.
Yes, yes. Don't worry about the class note. I will send.
Okay, sir.
Okay, I will send. Okay, thank you. Or any more query?
No, sir. Thank you, sir.
Okay, thank you.
Thank you,
Thank you,
sir.
sir.
Thank you, sir.
Thank you, sir.
जो लास्ट में लिख दिया